Okay, good evening, everyone. Let me see what we have stopped last time. Okay, I would like to check everyone online. You guys can hear me, right? Last time we probably stopped here. Which slides? I'm a little bit lost of my memory. Can anyone remind me where did I stop last time? I guess probably here. Really? Right? Slide 20, right? Okay, good. Yeah, last time we talked about the perceptron learning. Basically, we talk about the multi-layer perceptron. Basically the feed-forward process. How do we individually feed data into such kind of equation, which is pretty simple. We have its very brief structure in the past. Then here we show that if we set learning rate equal to 0.1, lambda equal to 0.1, then the 8 iterations of feeding data into this neural network and how those weights are got updated. And after a number of epoch of feeding those data into this equation, and what will be the values of W0, 1, 2, 3 change over the epochs. And we realized that probably after 5 or 6 epochs, that means you repeatedly feeding the data into this algorithm. And each epoch, you finish feeding 8 data points into this structure and estimate the weights based on this gradient descent update. Then after 6 epoch, then the 4 weights get into a more stable statute, which is negative 0.6, 0.4, 0.4, 0.2. Okay, you guys can do the hand calculation by yourself. So we were talking about classification case because we consider actually a linear combination of input variable is actually the F. Remember here, it's a weighted average. Remember, yeah, it's a weighted average kind of here. So it's kind of linear combination of input variables. So the decision boundary is actually linear. Okay. So if we visualize it, so the decision boundary of this neural network or perceptron learning pretty much look like support vector machine decision boundary, right? So basically all the linear separation models, their decision boundary look like this. So for nonlinear separable problems, perceptron learning algorithms will fail because no linear hyperplane can separate the data perfectly. Remember, what do we do with support vector machine? If we have nonlinearly separable problems, yes, we use kernel function. We transfer data to a hyperplane, and we introduce slack variables to tolerate the possible further non-separable case after even you using the kernel to do the transformation. Okay. So this is this slide shows the non-linearly separable data. So actually, based on such kind of two-dimensional distributed data points, whatever linear decision boundary you draw across this area, you're unable to perfectly separate them. Okay. Then how does multi-layer perceptron handle this case? We introduce nonlinear activation functions and more hidden layers to do the data transformation. Okay. So we introduce hidden layers between the input and output layer, which serve as intermediary layers between input and output layers. Then we use nonlinear activation function like sigmoid or hypertangent. Okay. So multi-layer perceptron, or we say multi-layer neural network, can solve any type of classification task involving nonlinear decision surfaces. Okay, we build up two types of decision criteria. So this is one standard multi-layer perceptron, involves one input layer, one hidden layer, and an output layer. So can we apply the perceptron learning rule to each node, including the hidden nodes? What is the hidden nodes? The hidden nodes is here. Okay, so the previous perceptron learning rules we can apply because the hidden layer we didn't consider. We just consider a simple network structure, which has an input layer and output layer. But can we apply the perceptron learning rule to each node, including hidden nodes? So perceptron learning rule actually do the update of the weights by computing the error term, which is the error between y, the observed response, and the computed response based on your network FWX, and updates weights accordingly. Okay. Then the problem is if you have a hidden layer here, you don't have the ground truth for the hidden layer should be. Okay, you have the observation of y in the end, but you don't have a reference, the ground truth reference for the hidden layer here to do the updating or to compute such kind of error term to update the weights. So we can do approximate error in hidden nodes by error in the output nodes. Okay, we want to approximate such kind of error via the errors we obtained in the output nodes. And the next problem will be, we are not sure about how adjustment in the hidden nodes affect overall error. And also no guarantee of convergence to optimal solutions. Okay. So basically we will introduce the gradient descent and back propagation for the multi-layer perceptron training. First, let's look at some terms and its description. The first is the weight update. So for a multi-layer perceptron or neural network with multiple layers, the weight is updated based on its gradient. How the gradient is computed? The gradient is here, okay? The gradient is here. So the gradient is computed based on the loss, take derivative according to each of the weights you want to update, okay? And multiply the learning rate lambda, okay? So for all the weights across the network should be computed like this. Then how the error function, or some more frequently we call it loss function. Okay. So how the loss function computed? Here we just use the residual, sum of residuals. This TI is something we observe, and these F, okay, with the input a linear combination of all the X, that's something we estimate. Okay. Then we compute their residuals with data points from I equal to 1 to capital N. Then we get the average error or average of the residuals. So in neural network, the activation function f must be differentiable. Okay. And for sigmoid function, we take the differentiation of the sigmoid function will be described like this. Okay, it will be like this. Okay. So we will mainly focus on the stochastic gradient descent, which update the weights immediately after feeding the data points. Okay. So the very traditional gradient descent is you feed all the data into the network and compute and do one-time update of the gradient based on the average. But stochastic gradient descent is every time we fit in the data points into the network, then we do the updating of the gradients, updating of the weights. And there's also another strategy called stochastic gradient with mini batch, and that's we fit each small batch of data points into the network and do one-time updates of the weights. Okay. So for the output neurons, weight update formula is the same as before. Okay. So, and for hidden neurons, so output neurons is the output nodes in the output layer, and the hidden neurons means the hidden nodes in the hidden layer. Okay. So this is the basically the formula of calculating the gradients of the output nodes at the output nodes and hidden nodes. So next, we take a handwritten example or hand calculation example to understand how the gradient descent and backpropagation is implemented for training a neural network. Okay. We actually consider a very simple network structure for helping us to understand such kind of process. So in this example, we consider a 3-layer perceptron as well, with 2 input nodes, 2 hidden nodes, and 2 output nodes. It is a fully connected network, so all the nodes is connected with each other in a forward way. Okay, but the input and output nodes they won't connect each other, and hidden nodes at the same level they won't connect each other. Okay, so then we have 8 links between those nodes and 2 bias term adding into the estimation. So it's basically hidden nodes will be equal to activation function of a linear combination of I and W, okay, plus B, right? So it will be like this. So remember, when we do the training of neural networks, the first is once its architecture is determined, that means we have determined how many input nodes in the input layer, how many hidden nodes in the hidden layer, and how many output nodes in the output layer and their connections. Then next, we do the initialization. So basically, the initialization will be done based on all the weights, indicating the link strength between each of the nodes. So here, from W1 to W8, okay, they are all initialized, and as well as B1 and B2. Those guys needs to be estimated. They will be initialized. Value at the input nodes is given. Okay, they're X. Okay, so X. I remember last time, Kayan tell me like I can use this text. Okay, so basically X will be equal to a vector I1 and I2. Okay, and y is equal to a vector O1, O2 as well. Okay, so this is x and this is y. So they are both observed. We observe x and we observe y. What we want to is building up a network structure which accurately estimate y based on the value of the input x. So what we want to optimize? What to be optimized? What to be optimized in this network? The W, okay, which is the matrix of the weights, and B, okay, that's the bias, two bias elements, okay. All right, so then we have the initialization of all the conditions, okay. So based on the initialized the weights and the bias, we are able to do the first thing is by feeding in the value of x's, the I1 and I2, by feeding in the value of I1 and I2, that input 1 and input 2, we are able to estimate the value of output 1 and output 2 based on the initialized weights and bias, and we can compare our estimation and the observation, okay? Then we can compute the error. So before we can do any updates, first we need to evaluate how the current neural network look like, which is actually forward pass process. So we do a forward computation. So remember, each of the hidden nodes have two sides, and we make the input side the net and the output side the out. Okay. Then next, we are able to compute the net H1. The net H1 means something be fed into hidden node 1. Okay. All right. So it's something be fed into the hidden node 1. Okay. So this is net H1. So what is the thing to be fed into the hidden node 1? It's a weighted linear combination, a weighted average of the information we observed at the input nodes. So it's weight 1 multiply the value of the input 1 plus the weight 2 multiply the value of the input 2 plus the bias. Okay, it's a kind of linear regression form. All right. So based on our values observed in previous slides, it's 0.15 multiply 0.05 plus 0.2 multiply 0.1 plus 0.35 equal to 0.3775. Let's consider the activation function at the hidden nodes 1 is logistic or sigmoid. Okay. So its form is equal to 1 over 1 plus exponential to the negative value of its input. Okay. Then we just computed this net H1, which is something to be fed into the hidden node 1, is 0.775. Okay, then what we get the output here. Okay, which is this one. And we do the same thing for the hidden node 2, and we got its output is 0.5968. Okay. So remember, I bet some of students already got confused. So first you need to get net H1. Then this net H1 will be fed into an activation function. Then it will be equal to the output, the out H1, okay? So the net H1 is here, is at this point, and the out H1 is here, is at this point, okay? Right? Hope my writing is clear. All right, now we get the outputs from the hidden nodes. Things get easier. We just move forward. We consider this part now. We consider this part now. We have the value estimated here. We want to forward it to the upper node based on the next level of connections. So we use the net O1 to describe the information to be fed into the output node 1, which is net O1 here. Net O1, okay, net O1 is here. So net O1 equal to weight 5 multiply the output of hidden node 1 plus weight 6 multiply output of the hidden node 2 and plus the bias 2. So by plugging in the numbers we have initialized, it's 1.1059. Same thing, usually we set the activation function on all the nodes of the network to be the same. So it is also set to logistic. It is arbitrary choice, I should say, activation function setting. You can set it to any types of activation function you like. Okay. But usually we, based on our experience for the multi-layer perceptron, the activation function with logistic or hypertangent, and sometimes exponential, they're good, okay? So then next, this net O1 will be fed into this logistic function-based activation function. Then we get the output from the upper node, which we actually plug in this 1.1059 into this formula. And we get the output of the output node 1 is 0.7513. And we do the same thing for the output node 2, and we get its output is 0.7729. Then the first run of the forward pass completes what we observed so far. We observe that in output, based on current network structure, the output of the output node 1 is 1.10 something. And the output of the output node 2 is 0.75 something. Okay, then we will find out the output node 1 has a very big error because the observed value is 0.01. And the output node 2 is still has an okay level error, but still significant, is 0.2 something. And what we want to next to do is based on this error, we want to propagate this error back and to adjust the value of this weight 1 to weight 8 to make the network, its output produce a value close to 0.01, and the output node 2 produce output the value close to 0.99. Okay. Then next, we do the back propagation. We first computing the error. So we use the sum of the residual square, sum of the square of residual SSR. Okay. So it is written as this. The residual is the difference between our target variable, observed target variable, and our model output. Okay. And we take a square and we summate all of it and divide by 2. Then what can we compute based on the previous slides? It's output of the O1. Wait, 0.75. Oh, yeah, it's 0.75. My bad. Yeah, it's here. It's 0.75. It's not 1.1. 1.1 is the input fed into the output node. I would like to correct here. Okay. So the residual is observed value is 0.01 and the estimated value is 0.7513. And this is the difference. And we take square and divide by 2, we get 0.2748. And we do the same thing for the output node 2. Then we get the total error, which is these two parts add together. It's 0.298. Now we know the total error and we know how good our model is. Then we do backward pass. We need to update weights of neural network to make outputs closer to the ground truth. Then next step is we want to backpropagate what? Backpropagate the gradient. Okay, we want to remember the weights of the network is updated based on the gradient. Then we want to optimize the weights across the network. We actually need to compute each of their corresponding gradients. Okay, the gradient for weight 1 and the gradient for weight 5. And we do that for all the 8 weights. And then we do the update, right? Everyone has their own weight, own gradient. This is called gradient propagate. And another way of saying gradient propagation, backpropagation is based on the error term, error O1, error at the output node 1, and error at the output node 2. We can only first get the gradient for weight 5, weight 6, weight 7, and weight 8. Okay. And why that, later we will talk about it. Then based on the calculation of the gradient and updated them, and then we can backpropagate the gradient here for the weight 1 and weight 4. So this is called backpropagation. There's a procedure.
Sorry, how to calculate the gradient?
I haven't talked about it. No hurry. I just talk about the procedure. Okay. All right. So this is why we call it backpropagation. And now we talk about how we are gonna to using our hands to compute the gradients for this network training. So ideally, we are actually taking calculating the gradient based on taking a derivative for the loss function according to the variable we want to optimize, right? Here we use weight 5 as an example. That means we want to optimize weight 5. Okay, we take a derivative. And what is the loss here? The loss is the error total. Okay, and we take a derivative of this loss against weight 5. However, this cannot be directly obtained. Okay, the analytic form of this cannot be directly obtained. We actually need to apply a chain rule as this to do the next computation. So this derivative of E total against the wave 5 can be such kind of chain rule. So because these terms can be canceled out, right? But we don't cancel them out yet. We expand it. Then we have these 3 terms. Okay. Then we want to talk about the computation of these 3 derivatives to obtain the true gradient for the weight 5. So let's go a little bit more math. So we know that the E total is equal to 1/2 half multiply the target minus the output, take a square, plus 0.5 multiply target at the output 2. This is observed. This is estimated. This is observed, and this is estimated. Okay, so targets O is actually the Y we observe. The value we observe. And the out O, I didn't write O1 or O2 because they are just 2 different channels, is the value estimated by the NN. Okay. Then we compute the residual, take a square, add them together, the summation. Okay. All right. So let's go back. See what we need to compute. First, we need to compute the first derivative. We're taking derivative of the total error against the parameter output at the output node 1. Then we just take a derivative, right? Because here we have the parameter output at output node 1. What we do, taking derivative, everyone knows, right? We first need to take this at the front, so it will be here. And this 2 minus 1 and 2 multiplied 1 over 2 is 1, right? And there's a chain rule. The inside needs to take out the target, taking derivative of the out is 0, and this one becomes -1 here. Okay, then plus 0. The second term has nothing to do with the parameter output at the output node 1. This one is very straightforward, right? Let me recap you guys the college calculus. Taking derivative, okay. The x squared will be 2x, okay. X plus y then what is the what is this term? Can you guys tell me the results in this exercise? We have a negative x plus y squared, and we take this one, take a derivative according to x, then what it will be? It will be 2 multiply negative x plus y and multiply the -1. because there are two steps, right? First, we move to the first front. And second, we need to take the inside one out. The negative x plus y also needs to take a derivative. So it will be just -1. Okay, so there's a chain rule. All right. So if we align our language on this page, then everything will be easy. And we clearly get that the this derivative will be plug in the number will be 0.741. Okay, so the first derivative term we fixed. Then we go to the second one. Second one is the activation function. Now we back propagate back to the activation function. So the activation function at the output node 1 is a sigmoid, is a logistic function. It's 1/1 plus exponential to the negative of its input, net 01. Then we compute the second derivative. We take a derivative of this equation against the net 01. Okay. So it will be the outputs multiply 1 minus the outputs. Okay. And it will be 0.75136 multiply 1 minus this term. Okay. So why it is equal to this? Previous slides give you some hints. Okay. Okay. So we finish the calculation of the second derivative term, which is 0.186. Then we do the third one. Then we back propagate back to the weight 5, the link. All right, so the input is a linear combination of the output of the hidden nodes. Then we take a derivative of this term against W5. And the second term has nothing to do with the weight 5 and last one bias 2. So they are both 0. And the only thing left here is W5 itself becomes 1. Okay, then it will be the output H1 left. So it's actually output H1 is 0.59329662. Then we take them together. We take them together. So we have this term has calculated, the second term has been calculated, the last term has been calculated. We just plug in the numbers and multiply them together. Then we get the gradient 0.08216. Okay. And how we are going to update the wave 5? The observed value of wave 5 is 0.4. Learning rate is 0.5. And the gradient is 0.08216. So Howlin, you got it?
Yeah.
Okay, great. Then we can do that for all weight 6 and weight 7 and weight 8. All right. Then we finish. So every layer, we just need to pick one as example. The other procedures, they are the same. So weight 5, weight 6, weight 7, weight 8, they are basically the same. Just the numbers, they are different, but the formula will be the same. Okay. Any questions and comments so far? So basically, there are two tricks here. First one is we expand this guy with the chain rule. So it will be a 3 term multiplied together, they're equivalent. Okay. Then next, we can compute each of the derivative term and multiply them together to get the final gradient for weight 5. The direct derivative, we directly differentiate the loss function according to the weight. It does not work. Okay, we need to play such kind of trick.
I have a question.
Yes.
How do we know that the iteration rule is right?
What do you mean by
Iteration, the update rule?
the last one?
Yes.
This one?
Yes. How do we know the rule is right? I mean, why do we minus the technical object? Why can I plot them?
Yeah, you're right. So basically, the gradient descent, it has a formula we have talked that the weight in the next iteration is equal to the weight at the current iteration minus a learning rate lambda. Here I use this symbol, but they're the same meaning. Then multiply, sorry. Multiply the derivative of the loss according to the weight. Okay, so the gradient. The gradient here we compute, it is positive, but it might not be. The gradient has directions. It can be positive, it can also be negative. So if the error says our network weight is too low, then its propagate gradient will be negative, then it will be increase the weight. But here is kind of the weight needs to be decreased. So it's kind of a control model. The signal feedback is the error we computed based on our estimated and observed values. I think you made a very good comment. Yeah.
Thank you.
All right, so how about we stop here? We take a break, then we come back at 8. Then we will following up the more challenging backpropagation of weight from the hidden layer to the input layer. Okay. So you're going to yeah. Yeah, and also our school also offers activities like groups if perform well, projects to be included as so I would recommend you guys see whether you will receive that. But this is I asked that for you guys. Actually, it is not that meaningful because they can look at it. It's kind of consuming place. So you actually, for example, and also, for example, you have travel from campus to another place. The travel cost. The regular day, the day that needs to go. We have 题目就是那个 C， 它的会的这个东西我也做，所以到时候我们还有会上。那个你站的时候，在那个大楼，然后。然后我们就是但是好几个啊，对，然后我是不一样，类似的，到时候我会告诉你。我也是，我看你现在只有他这个报纸那你那个现在他那个是美这个反正我下周。
说的时候还是
也是有一点像是那种 哦，原来这个角度，快点是在这里。你想，我是上了一天，那你们不是上了这一天，那你已经上了那你没选择的关系。所以你当时咋想？我还以为是没下去。原来有在给上谁呀？你为啥不选？这个正难就选这个。 卷的出发点在哪里？我卷的出发点在于我来听一个最新的。我听了半天，说这边免费主要是可以看
你下次你就在肯定加了之后，你加了他以后，你给他发一句话，做人有一些，然后我再把它给删了。
计划是不是？下学期的需要，我们让这个老师推荐，我看了，然后说一下，我觉得什么性，我又推荐没，你看都。反正你的毕业。对，他确实好热情。
人都是有两类型，当你对他是有用的，这不是真正的热情。
赵宇就是那种不想和他。
他们每一家都有相同的，那我还好意思把它看成是这是我在这里才干嘛？以前的真是什么同学，我就是同学的。哎，我认为我同学在找他同学。
那个说法后来是我就大一的时候开那种垃圾会。我当时
我也收到了文
我玩个 ADC，上帮帮两帮，对帮帮我全部就没有办法。
反正我是来认那个无人问题，意思就是都像我告诉的感染时，
Okay, let's come back. Further talk about the propagation, back propagation of gradients from the hidden layer to the input layer so that we can update the weights between the input nodes and hidden nodes. Okay. So the idea is similar. If we use the weight 1 as an example, we want to obtain the gradient of weight 1. The direct way is we take the derivative of the loss, which is E total here, according to the weight 1. Okay, this one. But this is not doable directly. Then we use the chain rule to expand it. Then we will have 3 components. First, we take the loss according to the output at the hidden node 1. And then we take a derivative of output at hidden node 1 against its input. And finally, we take the derivative of the input into the hidden node 1 against the weight 1 according to weight 1. So the tricky part here is if you take the loss, derive the loss according to the output node at hidden node 1, it actually contains 2 parts. So this one is actually the derivative of error at loss at output node 1 against the output of the hidden node 1, and the loss at the output node 2 against the output at hidden node 1, because the hidden nodes, the output of the hidden node 1 are connecting to 2 nodes. Okay. So this is also a complexity. So if you have a broader network, then this one will have more components add together. So for example, you have 3 output nodes, then hidden node 1 connect to 3 output nodes. You probably add another EO3 and take derivative against the output hidden node 1. All right. So the calculation is pretty similar. We repeat the same story. But the trouble one is at the first step. If we go back to the previous slides, these 2 terms add together. They cannot be done immediately. Okay. So take a derivative of the loss at the output node 1 against the output of the hidden node 1. They cannot be done directly due to the same reason. We need to further apply a chain rule as this one. This one is calculable. Okay. This one is computable. So for every of this, it needs to have 2 steps of calculation. So how many things we need to compute? This one have 2 elements. We go 1 more slides. So this one has 2 elements. This one has 2 elements. So that's total 4. And this one and this one. Okay. So that will be 6. This one have 2 derivative elements. And this one, 1. Okay, so that's total 6. So besides the previous output layer to the hidden layer, the double, okay, of the computational tasks. All right. So for this one, we apply the chain rule. So it can be equivalent to taking a derivative of the loss at the output 1 against its input and multiply the derivative at the of its input against the output of the hidden node 1. All right. So this one will be directly plugging the value 0.718 and 0.186. I think that has been computed in previous slides. Yeah, 0.186 here and 0.741 here. The good news is you don't need to repeat the computation from 0, you can bring some of the previous results in, okay? Then next, the second term. Net O1, taking derivative net O1. So then the input of the output node 1 is a linear combination of the output of 2 hidden nodes. So weight 5 multiply output of the hidden node 1 and plus weight 6 multiply the output of hidden node 2 plus bias 2. So you take derivative of this term against output of the hidden node 1. What will be left? Just W5, right? This one will be equal to 0. This one will be equal to 0. And this is 1, okay? Taking derivative, and this will become 1. And so W5 multiply 1, so it's 0.4, all right? Then we have this 2 term multiplied together. So it's 0.055399, okay? And similarly, we can obtain this term, which is equal to negative value. Then we add them together and we obtain the first derivative term, which is equal to 0.036. And next, we need to compute the derivative of the output of the hidden node 1 against the input of the hidden node 1 based on its activation function, which is sigma. So its derivative is equal to this one, okay? Then it will be 0.593 to 699 and multiply this term, and it will be equal to 0.2413. And then we go to the last job, taking a derivative of the input of hidden node 1 against the weight 1. All right, so what is the formulation of the input for the hidden node 1? It's a linear combination of the inputs values at the input layer. So it's weight 1 multiply the input 1 plus weight 3 multiply input 2 plus B1, the bias 1. Then we take a derivative against W1, then what left is this I1, the input 1 value. Others will be 0, okay? Then we got this 0.05. Then we multiply these 3 terms together, we get a gradient. Okay, it's a smaller one, at 0.00043. And we update the weight 1, it will become 0.1497. So another interesting thing we observe in this example is what? If we get the gradient for weight 5, 0.082, and once you propagate back to weight 1, it's 0.0004. Okay? So this gradient is kind of vanishing. If we have multiple layers, steeper layers, the gradient disappeared probably after a number of propagation, becomes smaller and smaller. Okay, so that's why one challenging issue in deep learning is to handle such kind of gradient vanishing. And another issue is if we amplify the gradient from one layer to another, it will become very big value, and that is gradient explosion. And this is particularly significant in recurrent neural networks. All right, so we finished talking about the hand calculation of the gradient descent and backpropagation. Yeah, 0.5 is the default learning rate. So this learning rate is the parameter that you need to tune in developing a neural network. Okay. So 0.5 is usually very large. We probably set it to a 0.1 or 0.2 sometimes in real applications. Design issues in ANN, artificial neural network. So how many issues we need to consider to develop a neural network? The first is its architecture. The number of nodes in the input layer. For example, we have input and output and hidden layer. First, we look at number of nodes in the input layer. So we are talking about a simple case in the past that one input node per continuous or binary attributes. But how about categorical attributes? What does categorical attributes mean? It means x1 equal to small, medium, large. Okay, when you buy the clothes, the size, that x1 denotes size, then it will be categorical. And what is the problem? So this such kind of categorical, we cannot directly convert it to 1, 2, 3. Okay, it could not make much sense. You probably need to have k nodes for each category attributes with k values. So what you need to convert it is one intuitive way is you make the input node representing these attributes as 3. And each of the nodes indicate 0 and 1, indicating whether it is small, it is medium, or it is large. Okay, got my point? So it will become 3 nodes, 3 input nodes. Each one is binary. Okay. This one means small, whether it is small, small or not small, 0, 1, medium, and large. Okay. I apologize my writing, but you guys can get my meaning. Okay. If you listen carefully. All right. The number of output nodes in the upper layer, the same story. So for each binary class in classification problem, for each binary class, each node is actually 1 output. But for a k class problem, you probably need k nodes, and each node is a binary, indicate which class it belongs to. Number of nodes in hidden layer we have talked in the previous class, I remember. Okay. You can be, the number of hidden nodes is randomly initialized. It could be less than the number of the input nodes, or it can be more than the number of the input nodes. And initial weights and biases. The initial weights and biases, they are all randomized between a uniform 0 and 1. Or someone might like using a standard normal or truncated standard normal, that's fine. Okay, so it's basically random generator, generate the value between 0 and 1. Its value between 0 means no connection. Okay, equal to 1 means a very strong connection. So some characteristics of artificial neural network. First, multi-layer neural networks are universal approximators. That means ideally someone claimed that neural network can approximate any types of functions. But this is just some claim, it does not being theoretically solidly proved. Okay, it's just a kind of indication. But could suffer from overfitting if the network is too large. So neural network is very easy to be overfitted. Okay. And gradient descent may converge to local minimum. So it is quite common that your gradient descent is trapped into a local minimum. It does not return you the global optimality of those weights and bias. That means your weight and bias is kind of optimal, but not the best optimal, okay? And model building can be very time consuming. Training neural networks is indeed very time consuming. It can even consume hours, okay? For example, 7 or 8 hours. It really depends on the model size and the number of inputs. But once the neural network is built, its testing is just a forward computation. It's very fast. A neural network can handle redundant attributes because the weights are automatically learned. So if attributes are redundant, some of the connection will disappear. It is sensitive to noise in training data. So that's why sometimes people design denoised neural network. And it's difficult to handle missing attributes. All right, so I finish the slides of lecture 5. Then let's go to lecture 6. We won't really touching the deep learning theory, but we will go through some of deep learning concepts for helping you guys to get some sense of future if you have chance to take deep learning classes next semester. Brief concept of deep learning and computer vision. So first, let's talk about why deep learning is developed and needed. Definitely, nowadays, the deep learning typically means deep neural networks, okay? So all deep learning methods presented nowadays are kind of neural network because its architecture can be easily extended to a deeper structure. First, let's talk about some limitations of shallow models. So what does shallow models mean? Shallow models cover all the classical machine learning models for regression or classification models in the previous slides, previous lecture notes, okay? So that's all the models I have talked in previous lectures. They are shallow models. And some of the time, the shallow models may refer to shallow neural networks, which the most complicated structure is 3-layer perceptron. One input layer, one hidden layer, and one output layer. And sometimes intuitive extension of a 3-layer perceptron to multi-layer perceptron. That means you have one input layer, 3 hidden layers, and one output layer. People don't believe that's deep enough. Okay, it's just simply extension of multi-layer perceptron concept. So in shallow neural networks, people think that its capability of modeling highly nonlinear and complicated process is still limited. It is basically due to that just having one hidden layer might not be sufficiently or might not contain the better flexibility in modeling. Okay, so this is one. And second, to apply a shallow neural network, you need to well organize the data to a ready form. Because shallow neural networks does not have the capability to process the raw data into the form that is ready to be used by a neural network. Okay. What is that sound? Who is Lina? Your computer losing control. Huh? How about you just share your voice with others? Okay, that's fine. Yeah, and the third limitation. Every time when you want to use shallow neural networks, you have to prepare the data in a ready form, especially like to do the standardization for all the dimensions. Okay. The next is the selectivity invariance dilemma. So the shallow neural networks does not have such kind of selectivity invariance capability. And this we will talk about later when we introduce the convolutional neural networks for computer vision. We will talk about what is the selectivity invariance dilemma. And last one is the backpropagation and the gradient descent might not be effective to well-trained perceptron with a large number of hidden layers. So that means if you're just stacking your neural network with many hidden layers, I think that person is walking. It's kind of walking sound. Okay. And the gradient descent might not be effective. This I have introduced like the gradient propagation will lose its function. Okay. Okay. That's good. I can mute that guy. Oh, it's tough. The next, I would like to talk about the selectivity invariance dilemma. This is majorly happens in image and speech recognition problems. In those problems, we usually require model to be insensitive to some irrelevant variations of the data, but sensitive to some relevant variation of the data. So what are the irrelevant variation of the data? For example, in the images, the same object, but its position, orientation, and illumination of the same object, they should not matter in our decision making or in our model. And in the speech recognition, the variations in pitch or accents of speech, they should not be mattered. While our models should be sensitive to minute variations like white wolf and breed of wolf-like white dog. Okay, so kind of things. Let me give more example using Google Scholar. No, just using Google website. Okay, so for example, we look at the photo of dogs. So basically, we can see like if we want to develop a neural network model to identify dogs from images. Okay, so we want our model to be sensitive between dog and the background items or background objectives. For example, these parts, this person. Okay, but we want the model to be not sensitive to changes of the dog position, pose, and orientation. Okay, so we should say this is dog, and this is also dog, 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 dog. Okay, so this is called selective invariance. We focus only one thing to be selective, but others we treat them irrelevant, like invariance, like does not matter. How the other things change, I don't care. I care about whether it is dog. Okay, so this is called selective invariance. And if it is a shallow neural network, the dogs in this image, if you don't have a very carefully developed features of images, then the network will classify this is one type of dog, this is another type of thing. Okay, so they won't recognize they are all dogs. They think they will be different. Okay, this is called selective invariant dilemma. But I actually didn't share this screen. Weird. I'm sorry. Yeah. Let me quick go through what I've talked. For example, here they are the dog images. The selectivity invariance dilemma means we want the model to be selective between the dogs and other objects rather than within dogs. Okay. For example, we want the model can identify dog from humans in this image. Okay, but we don't want the model to be different, identify like the dogs in different images, they're different. This is called selectivity invariance. Yeah. So how can we achieve that? So to achieve that goal, the shallow models typically need a very good feature extractor. That means we need to try a lot of image feature template. For example, in the past, in the traditional image processing, there have been a lot of discussions about templates for extracting feature from images. Like, for example, the textures in these images. Okay, different filters. All right, and like and some famous one like highlight features templates, which do feature development based on comparing the contrast, pixel contrast in the image. So we need to try different ways of engineering features from the images. All right. Then we carefully select appropriate ones so that shallow models can handle it. So one that produces representations that are selective to aspects of image important for discrimination. That means the aspects that are very important in our discrimination of the objects, but irrelevant to irrelevant aspects such as the pose of the animal. And generic features like Gaussian kernels do not generalize well for far from training examples. And handcrafted good features require engineering skills and domain expertise. Basically, some people who has been working in image processing with handcrafted features for many years, once they got one image, they know the way that for developing good features for that images. But for a new person, it could be time consuming. You need to try. It's basically a trial and error process. Deep learning offers new discipline. Deep learning targets on automatically learning representative features from the images. That means we don't refer to any design problems. We're just using one automatic process for learning representative features. And let's talk about some features of deep models. I mean, here the features means advantages of deep models. First, deep model is computational, composed of multiple processing layers. It's deeper. So it learns representations of data with multiple levels of abstraction. What is multiple level of abstractions mean? In an image, original data, each element in the image is a pixel. And the convolution is a weighted average process. Okay, the kernel in the convolutional neural network is a set of weights. So we're actually taking the weighted average of pixels in a patch. Then what is the weighted average of pixels? It becomes a mosaic, right? A lower resolution mosaic, but has a higher level of information summary. So you gradually apply convolution and to make more abstract but high level features, which can later be utilized as very strong supportive information for later classification or regression. Okay, and dramatically improved state of the art. This is a deep model has shown many successful stories in following applications. The speech recognition, like here, if you have iPhone, then that's the Siri, okay? So you speak one English sentence and Siri might highly probably understand what you mean if your accent is not that bad, okay? So that means it is, selective invariant. Different people with different accents tell one similar sentence, the model can understand. Visual object recognition, object detection, and other domains in medical, drug discovery, and genomics. The deep models have all proved their advantages. And deep models discovers intricate structure in large data set. So using backpropagation to update parameters and compute representation in each layer from previous layer. And the deep convolutional neural networks, mainly for image processing and video speech parsing, and recurrent nets, majorly for sequential data and majorly for text as well as the speech recognition. And next, I would like to talk about one key function of deep neural networks. What they majorly do is they do representation learning. Why we say representation learning? If we look at one image, imagine how big, if an image is kind of 400 by 400 resolution, then how big this data it is. So for image, an image is composed of pixels. If it is 400 by 400 size, that means it's a matrix of 400 rows and 400 columns. It's 400 multiplied 400. And remember, each image has 3 channels, which is the color channel, red, green, and blue, and multiply 3 if it is in RGB format. And the total dimension is this big. Okay. And if it's 1000, even a more higher resolution image, it is much larger. Okay. So such kind of big input cannot be easily processed by a shallow network. So what we do is we definitely need to learn a representation with a low dimension of this high dimensional input. This is the thing we typically want to do. So methods that allow a machine to be fed with raw data to automatically discover representations needed for detection or classification. So the common idea of deep learning is now always given a very high dimensional input. We learn a low dimensional embedding, or sometimes we call low dimensional latent features representing the raw input, and using these low dimensional latent features and as the input for the next regressor or classifier. Okay, that's basically deep learning recently do. So deep learning methods are majorly representation learning methods. They use multiple levels of representation, composing simple but nonlinear modules that transform representation at one level into a representation at a higher, slightly more abstract level. Based on deep learning, such kind of structure, more complex functions can be learned, and higher layers of representation amplify aspects of inputs important for discrimination and suppress irrelevant variations. So that's using image as an example. As I have introduced, input is an array of pixel values. So the first stage is presence or absence of edges at particular locations and orientations of image. So you're first taking average of the pixels as a mosaic. Then the first stage presents is each average square present an edge. Okay. And you further taking weighted average of those edges together. Then the second layer detection is the motifs by spotting particular arrangements of edges, regardless of small variations in edge position. You do a further weighted average of those motifs, then the third layer assemble motifs into a larger combinations that corresponding to parts of familiar objects. Then that would be the very informative features for later doing classification regression. So subsequent layers will detect objects as combination of these parts. And the key aspect of deep learning, so these layers of features are not designed by human engineers. So they are learned from data using a general purpose learning procedure, okay? So they are automatic. So next, let me talk about the gradient descent problem. So in a shallow neural network, we concern one important issue in gradient descent, that it is tracked by local minimum. Okay, we're afraid of that our gradient descent cannot return a global optimal of those weights and bias for us. So in the gradient descent, the objective function is always the average over all training examples. Is a hilly landscape in high dimensional space of weight values. So if we consider high dimensional input, it is not 2 or 3, it is like 100 above dimension. And think about the landscape of such kind of high dimension. It's a very hilly landscape, okay? And this 3-dimensional space, you can see already like this. So the negative gradient vector indicates direction of steepest descent, taking a closer to a minimum. And the goal is to learn the weights from a labeled set of training samples. And we have talked about the gradient descent. So we know that in the shallow models, we are afraid of gradient descent cannot give us good optimality exploration that is local, easily to be trapped into a local optimal. Therefore, a new strategy called stochastic gradient descent to be proposed. So the stochasticity is introduced by just taking individual data or a mini batch of data as the input to do a computation, so that you are able to. So if it is the global optimal, the stochastic gradient descent is like fluctuating like this. So due to the fluctuation, you are able to escape from the local minima to move towards the global minima. Okay. So so this sentence I don't want to repeat. You guys just read, okay? So the stochastic gradient descent is just like the fitting strategy is not the whole batch of the data points, but a small portion of them, okay? So it is called stochastic because each small set of data points returns a noisy estimate of the average gradient over all examples. It's spiky, so we say it is stochastic. All right, so let me see. Okay. All right, so we stop at the SGD and take a break. Then we come back to talk about deep learning architectures. Okay, let's continue about our introduction of deep learning today. Okay. So one typical deep learning architecture is to stack multiple layers of single modules, and all those modules are utilized to serve for learning nonlinear input to output mappings. Okay. So each module transforms input to improve both selectivity and invariance of the representation. So we want it to be selective and invariant to some irrelevant part. So with depth of 5 to 20 layers, can implement extremely intricate functions of input. That means very sophisticated functions of input. And since so we want to make the whole model sensitive to minute details. For example, distinguish Samoyed, which is one duck, from white wolves. Okay, but insensitive to irrelevant variations. For example, the background of the image, the pose of the duck or wolves, and the lighting of the camera shooting conditions, and surrounding objects as the noises. We want our models to ignore all those factors, but sensitive to minute details to distinguish the objects that we are interested in. So what is the big problem of deep learning than the traditional shallow neural networks or shallow model learning? So in low dimensional problem, which we usually face or solve by shallow models, we worry about the GD got trapped in local minima. Thus, we have a stochastic gradient descent developed. But we find that even in high dimensional problem, the stochastic gradient descent will lose its function. Why? Because there's a new problem called saddle points show up, okay, in a deep learning scenario. So in local minima is rarely a problem with large networks, okay, although, so it does not mean that the local minima has been solved. It is just because the saddle points become more severe than local minima. So usually in large networks, we worry about the techniques for solving saddle points rather than local minimas. So regardless of initial conditions, system always reaches solutions of similar quality, and the landscape is packed combinatorially large number of saddle points where gradient is 0, and almost all have similar values of objective functions. So this is the problem, the three aspects that the deep neural networks will fit, okay, will meet. That means the saddle points problem cannot be well addressed by different initialization technologies, because whatever initialization you applied, the neural network will always reach solutions of similar qualities if you cannot well address the saddle points problem. So let me draw what is the saddle point problem. For example, move it here. Move it here. So one classical example of the saddle points is like this. It's like this. So the contour will be like this. So what does this contour mean? If we start from here, This is the starting point. And what is probably the minimum? It's probably here. Okay. The global minimum probably here. Then what is the problem if we apply SGD or gradient distance based methods in this example? At the beginning, the gradient distance can lead us downgrade, not downgrade, walk down to a area. And the set points is a set of points has no gradients. That means these places is just flat. Okay, this place is just flat. And no matter you move left or right or forward or back in this area, they all return no change in your loss function and no gradients computed. A gradient equal to 0. And what the algorithms or what the models will believe. Okay, it sounds like we converge. We should stop there. But the problem is you haven't reached. It can be further down. If you go further, then we'll go further down to the global optimal. But the problem is you already lost directions here. Okay, so this is the setup point problem. So some approaches to address such kind of issue. So we know that the setup point is usually induced by a high dimensional problem. That means your input has a high dimension. Or the number of parameters involved in your network is very large. Okay. Then what should we do is we can actually do a pre-training. So we start from 0 to gradually grow a network. Very deep is very difficult. Then how about we do some pre-training with an unsupervised learning scheme to develop hidden layers stacked in a deep network. So these methods will include like autoencoder and deep autoencoders. Okay. Then once the architecture is determined initially based on this unsupervised learning process, then next we, on top of the problem, we assign in the output, okay, the output layer of the network, then apply a supervised learning to fine tune the network, which is a regular backpropagation, as we have talked. Okay, so this is called two-stage semi-supervised learning. So what is an autoencoder network look like? So the autoencoder is a deep neural network with a very specific architecture. It's like a butterfly. So it has like different neurons. This is just an abstract description. Okay. It could be a butterfly wing. That means you start with a very high dimensional input. Then you do a low dimensional embedding. Okay. You convert the high dimensional input to a low dimensional, to lower dimensional, then finally to a very low dimensional bottleneck. Then you have a decoder which exactly the symmetric inverse of this encoder. Then you do the reconstruction of the input. Okay. So the autoencoder is given a set of the inputs where this network we are able to return a very close reconstruction of that input. It's kind of generation process rather than regression, rather than classification. It is a new concept of unsupervised learning. We want to rebuild the input. So what people have hypothesized in this network architecture, people hypothesized that if we are able to learn an autoencoder successfully reconstruct the input we have in this model, that might indicate that we have clearly learned the mathematical mapping among those inputs. Okay. And this is you have learned accurate mapping among those inputs so that its inverse can return you very accurate reconstructions. Okay. So this is autoencoder. And autoencoders, they are usually deep, okay, because that means you stack a number of hidden layers in the encoder and also the decoder, okay. And if you work on computer vision, there's a very famous network called UNet for segmentation. And this UNet is a kind of autoencoder structure. Okay. And next we talk about the convolutional neural network. In deep learning, basically nowadays people talk about two very famous type of deep networks. One is called convolutional neural network. Another is called recurrent neural network. Okay. So for convolutional neural network, it's like DCNN, okay, deep convolutional neural network. And the other famous architecture is like ResNet, AlexNet, and DarkNet 53. And there are different architecture for convolution. And the recurrent neural network have its famous variants. Its variants name are even more famous than INNs. They are actually LSTM, long short-term memory, and also recurrent gated units. Okay, yeah. Gated recurrent units is GRU. Okay. So first, let's look at the convolutional neural network. First, is this a type of deep forward network? It is much easier to train and generalize much better than networks with full connectivity between adjacent layers. It is easy to train because the convolutional neural network, they connected with the kernels. Okay, the kernel is a kind of local matrix of weights indicating local connections among some nodes. Okay, so they are not fully connected. So what does a fully connected convolution network look like? So if I assume a set of nodes, they're kind of here. Okay, so a fully connected is that every node connects to the next four. Okay. So what does convolutional do? So convolutional has a kernel, okay, to weighted summarize these four, and weighted summarize these four, and weighted summarize these four, weighted summarize this four. So it is not fully connected, it's just partially connected. Okay, and it returns also kind of four nodes next. Okay, it's just this four into one, and this four into another one. Okay. All right. So it is not fully connected. So it is designed to process data combined in the form of multiple arrays. Or nowadays, we even say it's like in the form of tensors. So a color image composed of 3 2D array of pixel intensities in 3 color channels. Okay. And many data modalities are in the form of multiple arrays. So one-dimensional array for signals and sequences, including language, two-dimensional for images and audio spectrograms, and three-dimensional for video or volumetric images. Okay. So 4 key ideas behind convolutional neural networks. the CNN take advantages of properties of natural signals. The 4 key advantages of properties is first one, using kernel to build up local connections. And the kernel, they have shared weights. So for example, if I do convolution, assume I have an image of 9 pixels. Okay, so I set up a kernel which is 2 by 2, and its weights is like 0.2, 0.3, 0.1, 0.4. And this 2 by 2 kernel is applied everywhere, and these weights are shared by all the kernels when you do the screening. So it's a little bit abstract here, but if I draw another neural structure, then you will understand. So if 9 pixels, I treat them as 9 nodes, and each kernel has 4 weights. There are 4 links, so it's weighted average of them to 1. Okay, then weighted average another 4 to another 1. All right. So this is convolution, and you build up another 4. So it is not fully connected. So this one never connect to this node, and this one never connected to that node. Okay, so it's a local connection, but the weights, they're similar: 0.2, 0.3, 0.2, 0.3, and 0.1, 0.4. So they are shared. So what you want to optimize is just this, the weights of the kernel. Okay, and you have a pooling layer, and this convolutional layer can be stacked for many layers. So the convolution in deep learning, they mainly exploit the local properties. They focus on the local spatial relationship, so that the network should exhibit invariance to translation, scaling, and elastic deformation. Okay. The shallow neural network ignores a key property of images. So nearby pixels are more strongly correlated than distance one. And modern computer vision methods exploit this property. Okay. And information can be merged at later stage to get higher order features and about whole image. The higher order features means more abstract, more informative summary of those individual pixels at the beginning. Okay, so this is CNN inspired by visual neuroscience. It's like the human first as a retina and LGN, and becomes V1, V2, V3, and so kind of it's kind of a biological process. So from the machine processing, it's a kind of 3 mechanisms of CNN. First is called local receptive fields. Local receptive fields is kind of, for example, 9 by 9 or 3 by 3. Okay, you determine the local perceptive fields you would like to compute. So a lot of tuning in CNN is tuning the kernel size. Okay, and subsampling, which is means pooling, and weight sharing. That's 3 key mechanisms. Yeah, this is an illustrative example of the convolution and the subsampling. Okay. So first you have an input image, you do convolution. Okay, then you build up a convolution layer. Okay, then you using a 2 by 2 layer, then you build up subsampling layer to do a further subsampling. So instead of treating input to a fully connected network, 2 layers of neural network are utilized. First, the layer of convolutional units, which consider overlapping regions. And the second is the layer of subsampling units, make them as different non-overlapped areas. And several feature maps and subsampling, the gradually reduction of spatial resolution compensated by increasing number of features. And the final layer has a softmax output and the whole network trained using backpropagation. So in convolutional neural network, we typically don't do with the signal activation function. We're typically using ReLU activation, which is a kind of more linear form. So weight sharing, I have already talked about it. So I probably skip that one. So this is examples of how the convolution works. So you have individual pixels at a raw image. The image have 3 channels. One is the matrix of the red color reflected in each of the pixels, and the green color channel, blue color channel. So for each of the channel, we do convolution, then we stacking them together as a kind of channel matrix. Then we do a max pooling. Max pooling is just you take the square of pixel values and you take the maximal one. Okay. So what is pooling? I use a very simple example. If we have a patch, which is small of image, have 4 pixels, and in each element, yes, like 0.4, 0.1, 0.2, 0.3. There are a number of ways of doing pooling. One is called max pooling. So max pooling is just taking the maximal value among this matrix, which is 0.4. Another is average pooling. You're just taking average of these 4 elements, okay, as the outputs. And this convolution and max pooling can be stacked layer by layer, and finally you get a large number of highly abstract latent features. So the architecture of a typical CN, the structure as a series of stages, and the first few stages are composed of 2 types of layers and a nonlinearity. So first is 2 types of layers. One is convolutional layer to detect local conjunctions of features. And another is pooling layer to merge semantically similar features into one. And nonlinearity is the ReLU as an activation. Okay. So this one, convolutional layer unit is organized in a feature map, and each unit connect. So this I have talked about it. So the pooling layer is actually computes the maximum of a local patch of units in one feature map. And neighboring pooling units take input from patches that are shifted by more than one row or column. Okay. So what does that mean? If you have so the pooling 2 by 2 will be shifted by one row or one column, and to repeat this 2 by 2 operation. And all the CN structure is actually very simple, can do backpropagation, okay, with a gradient descent. It will be like a regular deep network. It is doable mainly due to a number of convenience we have set up in convolutional neural network. First is the weights. They are shared, okay, across different kernels. Okay. And also activation function, they are the same. We set all activation function as ReLU until the last one probably is softmax or other due to the regression or classification task. So next we go through the concept of recurrent neural network. First, we start with the vanilla one-to-one neural network, which recurrent neural network, which is like this. You have an input node, and you have a hidden layer, and you have the output. So recurrent neural network have different structures and due to different process of sequence. And we have one-to-one. So we have one input and one hidden layer and one output node. We have one-to-many or one input units, and we generate a sequence. Then we have a sequence of many elements where the recurrent structure to embedding it to one unit. And we have a whole process with a many-to-many structure. And as well as we have this kind of no shift many-to-many. This is more like forecasting. Okay, it's more like time series analysis. And this is directly video classification, direct video, many-to-many structure. So recurrent neural network have a basic expression. Its hidden layer is very simple. Recurrent, the math is very simple. It's a activation function composed of one of its previous hidden layer and the current input of the current input value, and it embeds to a hidden layer. So basically, this function can be described as a, let me draw better, as one hidden node at t-1 moves into okay. So this is the recurrent unit structure. So the recurrent is every HT, the hidden layer, hidden units or hidden layer is computed based on its previous hidden layer and the current input. So this recurrency reflect here. Okay. So for example, the activation function is hypertangent, then it is computed based on a linear combination of the weights multiply the previous hidden layer and plus the weights multiply the input. And they are embedded into a HT, the hidden layer at T. Then according to a fully connected network, then we got YT, okay, this YT. And this is weight from the hidden layer to Y. And this is the weight from the X to hidden layer. And this is the weight from hidden layer to hidden layer. Okay. So the computational graph of recurrent neural networks is like this. And one commonly applied techniques for saving computation is also the weight sharing. And it's majorly shared between the previous hidden nodes to the activation function and to the next hidden node, hidden layer, okay? And this is computation many-to-many case, many-to-one case, one-to-many case, many-to-many, many-to-one, and plus one-to-many. It's a kind of encoder-decoder RNN, okay? So RNN was famous for a short while, but later got dominated by its variants. This is because two big disadvantage of vanilla recurrent neural network. Vanilla recurrent neural network means the genetic generic version. First is iron suffers from serious gradient vanishing and exploding problems. And it cannot process very long sequence if activation function is hypertangent, because the previous memory will quickly lost due to its a simple recurrent structure. And it is very unstable if activation function is ReLU, and difficult to be stacked into very deep model and cannot handle very long dependencies. There are two very famous variants of recurrent neural networks. One is the long short-term memory, another is gated recurrent units. Okay. But we don't go details about the STM and GIU. You probably will learn it in other courses. What else? The transfer learning will be a long story. We probably stop here. How about today? As you guys look tired and there's no one to listen anymore. Okay. All right. So thank you very much for attending. So next we will finish the remaining contents in transfer learning. Then we will go to some industrial applications of using data-driven models. So we'll talk about a number of smart city applications like renewable energy transportation and medical healthcare. Okay. All right. So we will end up here. See you guys. Bye-bye.